Hello everyone, we are Team Phoenix Electric, and this is the Annunciator, a continuation of a capstone project that was initially started in the fall of 2020. Our technical directors include Sandro Silva, the Director of Engineering at Phoenix Electric Corporation, and a URI graduate of 2002, along with Mike Smith, our Capstone Consulting Director and URI graduate of 2001. Our team consists of two engineers, myself, Nicholas Kostick, an electrical engineer on the left, and Daniel Wilkins, a computer engineer on the right. This project is sponsored by Phoenix Electric Corporation. I've included their mission statement here, which reads, to provide our customers in the electric power industry the customized solutions and technical services they require to meet their individual power needs. Phoenix Electric Corporation is one of the world's top suppliers of air core reactors. They are responsible for retrofitting over 50% of America's hydropower switchgear, as well as offering custom engineered controls tailored to the needs of utilities. As it was one of my first questions upon entering this project, you might also be asking, what exactly is it that we're building? When an electrical process out in the field exists, how can you monitor the health of those signals? This is where the Annunciator comes in. By connecting up to 48 individual signals to the Annunciator, we can monitor such health signals. If something goes haywire and the process signal is lost, the Annunciator would immediately see this and trigger a fault for that specific channel. In addition, an audible alarm would enable, alerting nearby personnel immediate attention is required. The Annunciator will be a commercially available product sold in different configurations. There will be a 48 channel, 36 channel, 24 channel, and 12 channel version of the Annunciator. To gear this product for commercial and industrial use, the Annunciator has been designed to be a rack mount device. There are many motivations for such a product to exist. Phoenix Electric believes that there exists a gap in commercially available Annunciator products. By developing a first-party solution, this allows Phoenix Electric three major advantages: decreased reliance on third-party manufacturers when providing custom services, full control of the vision on what an Annunciator should be, as well as expanding their market share in the power and control commercial space. Working with Phoenix Electric Corporation, our team will create an in-house Annunciator system that will provide Annunciator panel options at lower costs, greater user configurability compared to existing products, and control over the hardware makeup of the product, guaranteeing quality and ethical responsibility. For the Annunciator project, the goal is to present a functional prototype of the Annunciator system that would be functionally equivalent and reliable in comparison to current options available on the market at a significantly lower cost. This year's anticipated best outcome can be broken down into two categories. The electrical and hardware outcomes involve prototyping and fabricating a custom power converter that will power the Annunciator on a wide range of input voltages. Also, providing updates to existing PCBs while expanding their functionality, and expanding flash memory capabilities to increase future reliability. The computer and software outcomes involve updating the graphical user interface, or GUI, to fit within modern industry standards. This includes a rewrite of the embedded code to focus on a clearly defined structure. Also, incorporating various predefined alarm sequences, enabling end-user configurability, and prototyping and implementing Modbus communication between the GUI and the Annunciator. As a team, we made many accomplishments this semester towards the ABO. For the electrical and hardware side, a system power requirements analysis has been done. The panel LED's brightness has been optimized. Power converter components have been researched and selected, which were then prototyped on a breadboard. The resulting configuration was transferred over to a fabricated PCB that was built and tested. Internal memory was upgraded. The panel also contains a new USB human interface solution, and work has begun on updating the existing main PCB to incorporate the above changes. On the computer and software side, an assessment of the legacy software was completed, which led to the conclusion a complete code rewrite was required to reach the ABO. The GUI was rewritten using a strongly structured programming style, object-oriented programming. We added a virtualized Annunciator to the GUI, which allows the user to visually work with the physical model. The embedded code was rewritten to take vastly less space, 93% down to 38% embedded memory usage. In addition, a new communication protocol was developed for GUI to Arduino interaction. Finally, 3 completely new alarm sequences were added. After starting this project in September, Daniel and I had to familiarize ourselves with what the previous year's teams have accomplished. The idea then was to use a commercial off-the-shelf power supply to power the Arduino. The Arduino would then provide power to all the Annunciator components, mainly the speaker and memory chip, and the front panel LEDs. After an in-depth power analysis, it was found that powering 48 LEDs simultaneously from the Arduino quickly approaches the current limit of what the Arduino can handle. This has the potential to create dangerous results. To solve this problem, power distribution had to be reimagined. With this new system, the Arduino would still provide power to most of the internals, including the memory chip and buzzer, but the idea is to isolate the LED power from the rest of the system and power the LEDs directly from the power supply. To meet these new power requirements, a custom power converter would be designed. As shown here, the converter must be able to take an input of either 120 volts AC or 125 volts DC and output to 2 unique power rails, 5 volts DC to power the LEDs and 9 volts DC to power everything else. Breadboard prototyping began with this converter after initial design considerations. Commercial off-the-shelf converters from reputable power electronics companies were selected to handle the conversion, pictured here. With the future goal of getting this design UL certified, additional circuitry was added for immunity and emission requirements, as well as filtering. Many versions of this prototype were realized before this final one you see in front of you. To verify functionality, a 125 volt DC power supply was input to the circuit. As you can see, approximately 9 and 5 volt rails are output. After verifying functionality of the design, it was time to realize a more permanent solution, a PCB. The goal of the first version was to make the board as component dense as possible. This version was created before I had a solid idea on exactly where the board was going to be mounted. Unfortunately, this is not realistic, as this board would be plagued with arcing and EMI issues. In version 2, component spacing considerations were priority. The AC and DC side were completely separated. In addition, the individual component spacing was significantly increased. This version is the third and final. Its shape is a result of the location in the chassis that it will be mounted. A slot was added to further separate the AC and DC sides of the board, and the input and output headers were finalized. Shown here is the final product of the power converter. It was tested here using a 125 volt DC power supply, and it successfully powers the Annunciator. It was also tested using 120 volts AC with identical results. Unfortunately, supply shortages due to COVID have greatly impacted the Annunciator project over the last 2 years. The current memory solution was selected during such time, which involves a voltage level shifter to operate. With supply making a comeback, the solution was reevaluated and a new memory IC was selected that doesn't have this requirement. I was able to double the memory capacity while simultaneously reducing cost. This is accomplished by the removal of the level shifter and associated passive components. The brain of the Annunciator lies here, on the main board. Modification had begun to incorporate the previously stated changes. These changes include removing the unnecessary memory circuitry and reworking the power distribution in anticipation for the custom power converter. Additionally, a fourth push button was added, which will enable new Annunciator features such as alarm silence. Lastly, the Arduino was moved to a new location and a cutout was added. This is to accommodate a new front panel USB interface solution, shown here. For the spring semester, there are a few electrical tasks left to handle. First, I would like to verify and test fiber and Modbus hardware functionality to ensure proper operation. Results of this testing might require further modifications to the main board. Additionally, the LED display board needs updated resistor values to reflect brightness optimization changes. Further tasking will involve the exploration of additional features that will increase both quality and performance to the Annunciator. I'd like to now introduce Daniel Wilkins, who will discuss the computer and software advancements made this semester.
Thank you, Nick. As a computer engineer this semester, I worked on a complete rewrite of the microcontroller's embedded code. In addition to keeping all the legacy features from last year's hard work, we also implemented new alarm sequences, a new data structure, and a robust communication protocol. We also worked on modernizing the GUI with a user interface and user experience overhaul, and we brought it up to date with the microcontroller communication protocol. For the embedded code rewrite, we developed a data structure using a highly stylized approach. This included using object-oriented programming for setting up classes. We also used input processing output pipeline for data management. And using both of these techniques, we were able to reduce the effective size on memory by around 60%, which provided much room that was needed to implement the new features. So one of the first features we tackled was the alarm sequences. We reworked all the legacy alarm sequences, including the A, F1A, F3A, M alarm sequences, and we added 3 additional ones that were completely new to the project, that being the F2M1, R, and R129 alarm sequences. Here you can see the data map used for developing the embedded code and the graphical user interface. And you can see the pathways that communicate between them marked in orange. The Arduino is marked in green, and that will output to the Annunciator, the physical version, and it will also send data to the GUI. The GUI, marked in blue, will send data to the virtual Annunciator, and it would also send data over serial communication to the Arduino. This is the depiction of the virtual Annunciator for the GUI. This provides an interactable version of the Annunciator for configuring the alarm channels and viewing the alarm sequences on the computer. Each channel you can select and it will allow you to edit the configuration for it. You can also select multiple, or you could select them all at the same time to modify a bunch of channels simultaneously. The virtual Annunciator, shown on the last slide, will provide a live stream of Annunciator alarm sequences. That being the LEDs that flash on the Annunciator will show up on the virtual one to allow greater user control. This will also serve as an intuitive menu for alarm channel modification, where you will have access to change the delay time per channel. You will also be able to change the normal status of each channel, and also the horn toggle to say whether the horn should be enabled or not. This will eventually also serve as a hub for additional Annunciator information, such as metrics, log files, and user labels. I anticipate being able to expand to the GUI in the future to expand to a metrics page. We will have graphs showing Annunciator activity. We will also include this to the log file system, which will store the log files on the Annunciator itself and display it on the GUI. We will also add Modbus integration, which will have to have a embedded component as well as a GUI component to allow for communication over both of those systems. Team, our primary focus for future technical accomplishments is implementing and testing Modbus communication. We will test both the software side and the hardware side. We will also continue development on the GUI to deliver new ways of user control. And we will explore implementation of additional features to improve the quality of the product overall. Over our development time this fall, we evaluated several risks that we estimated to be threats to the project. Using a grading scale that goes off of likelihood of the risk happening and seriousness if the risk should come into play, we were able to assign scores to the following risks. We believe that the power supply might have a failure, which would decrease sales and customer trust with PEC. We believe this has a very low likelihood of happening, but has a very high impact, so we assigned it a C grade. We also believe that chip shortages might impact our assembly of future boards. So we assigned a likelihood of high because this is currently happening in the market, and a seriousness of medium because we know that in the case that any chip has gone out of stock, we can likely find a replacement that will be similar. So this was given a B rating. And for a rewrite of all the software, we believed that development time of old legacy hardware or software might impede the addition of new features. But as most of the legacy software has been already reworked, we assign this a likelihood of medium and a seriousness of low, and it was given a D scale. To reach our ABO, we are highly confident that we will be able to present a functional Annunciator unit equivalent to current market options, and we will also be able to develop a GUI with features to access all of the Annunciator systems. And as a team, me and Nick would like to acknowledge and thank Dr. Harsh Sunak, the ELECOMP Capstone Director, for his great work in assembling this program. We'd also like to thank Sandro Silvia, the PEC Director of Engineering, who has worked with the company and has served as a mediator to deliver the expectations for this project. He's offered some great advice on which path to take this to provide the best anticipated outcome. And we'd also like to thank Mike Smith for his technical skills in directing this project. They have all been instrumental in our success so far, and we look forward to working with them in the spring semester.